Hello my dear students, this is Akash HD. Welcome to the ASD physics classes. Hope so you all are doing really great. So students, in this video we are going to see the further applications of Ampere's circuital law. In application number 4 we are going to see magnetic field of a solenoid, especially infinite solenoid and finite solenoid also. Okay, but infinite solenoid is very important. By default we will always take infinite solenoid. Okay, and after that in our next application we will see magnetic field of a toroid and we will solve so many questions also. Okay, so let's start the video. So here you can see, as this is the application of Ampere's circuital law. First again we will see what is the Ampere's circuital law. So in the Ampere's circuital law, what happens that here the line integral of the magnetic field for the closed loop, this is called the closed integral. So closed integral B dot dl, dl represents line integral, is equal to mu naught into I enclosed. And I have told you in which situation enclosed current will be positive: when we put the thumb along the direction of current and all the curved fingers along the direction of Amperian loop, then the current will be positive, otherwise the current will be negative. Okay, so now see here the application number 4, magnetic field of a solenoid. Okay, so how the solenoid looks like, you can see very well. Solenoid looks like this here. Yellow color is there. Now which path is there? Guess the path is the helical coil. Okay, so see here, a solenoid is tightly wound helical coil of wire over which an insulating material is coated, so that adjacent turns are electrically insulated. Remember that here adjacent turns should be what? Electrically insulated. Okay, now see, if length of the solenoid is large, okay, as compared to its radius, that means L greater than smaller, then it is taken as infinite solenoid. Okay, and after that see, inside the infinite solenoid magnetic field will be reasonably uniform, that means approximately uniform, and outside it magnetic field will be negligible, or we can tell 0. Okay, so infinite length solenoid, this is the approximation. Inside magnetic field reasonably uniform, outside we can tell negligible or ideally 0. Okay, now after that see here we are going to prove the magnetic field of a solenoid here. Okay, so see here, first see, let current I flows through an infinite solenoid and small n be the number of turns per unit length. Again I am telling, small n be the number of turns per unit length. Magnetic field inside the solenoid can be calculated by imagining a rectangular Amperian loop PQRS as shown in a diagram here. Okay, so this thing is there. And one more thing I will tell you here, I have told you small n number of turns per unit length. Okay, so let's take this solenoid is having the capital N number of turns and length of the solenoid is the L. Okay, so this small n will be how much here? Remember that here, this small n will be capital N by L. Capital N total number of turns and capital L is the length of solenoid here. Okay, this length of solenoid is how much here? Capital, is it? Now after that what will happen that here, let's take some current is flowing in the solenoid like this, is it? So when the current will come like this, see I, so here like this current will flow, is it, like this, and this we can write here what is flowing, the current is flowing here, and from here it will come outside, is it? So this is the solenoid. So in this situation what will happen that here this solenoid in a circuital form now, because to make it the simplified form we can represent this side here, is it? So this is the identical diagram is there. Okay, and you can see very well the current is going like this, that means upward towards you, downward away from you or inside the board. Okay, so like this current is flowing, is it? Like this current is flowing. So what will happen that here, when the current will flow like this, curl all your fingers along the current, then the thumb will indicate the direction of the north pole. That means what will happen that here, again I am telling, curl your all fingers along the current, then thumb will indicate the direction of the magnetic field. So what will happen that here, indicate the direction of a magnetic field, or we can tell indicate the direction of the north pole. So this is the north pole and this side is here south pole. Remember that here, like this. This side north pole, this side south pole. And you know very well, inside the magnetic field lines always from which pole to which pole? South pole to north pole. Outside north to south, but inside south to north, is it? So see, this is the situation. So this thing is represented here. You can see From all this, current is coming outside. Dot inside the circle means current is coming outside here. Cross inside the circle means current is going inside. Okay, and magnetic field. Which kind of magnetic field? Uniform magnetic field is there, and it is represented by the equidistant straight lines. Is it? And I am writing here this magnetic field is given like this here. See arrows. Okay, this is the magnetic field, south to north. See here, this is the south, and see this is the north here. Okay, so let's take the magnetic field is B, and this magnetic field only we are going to calculate. To calculate the magnetic field, what we have to do here? We have to take here the which loop? A rectangular loop, PQRS. Is it? So see here, I am taking here the some rectangular loop is there. Is it? So here, see, I am writing here. See the loop I have taken here. See, this I have taken here. Is it? Imaginary, no? So only we are writing here with the dotted line here. Is it like this? See, this loop I have taken here. Okay, and this loop, what you write here? This loop is a PQRS. PQRS. And what is the name of this loop? This loop is a Amperian loop. Again, I am writing here Amperian loop. Okay, and always make sure that always make sure that the direction of the Amperian loop you always take in the direction of the magnetic field. Then what will happen? The current you can take always positive, no problem here. Now, so you can see the current is going in, what to tell, magnetic field is going in which direction? This direction. So Amperian loop direction also I will take in the direction of the magnetic field. Okay, so see here, this is the Amperian loop direction, like this is there. Now this is the Amperian loop direction. Magnetic field right side, so Amperian loop also I have taken right side, no problem. After that, let's take here this length of the Amperian loop. How much here? Let's take the length of the Amperian loop is L. This length how much here? L, and this is also L, and this also you can take, no problem. Let's take I have taken rectangular now, so let's take here B. This is L, this is L, this is B, this is B, small b. Is it? You can take some other letters also, not at all problem. Okay, and sometimes question used to come like during the magnetic field calculation of the solenoid, what is the shape of the Amperian loop? So which shape is there? A rectangular shape is there. And how the Amperian loop is there? So how the Amperian loop is there? Some part inside, some part outside. Remember that they have asked in a question. Okay, now after that here we'll use the Biot-Savart law. So according to the Biot-Savart law, what we know that here, see, as according to Biot-Savart law, closed integral this B dot dl is equal to mu naught into I enclosed. Is it? Mu naught into I enclosed. Now after that here, which loop is there? The closed loop PQRS. Now, so we'll write here, see, I'll write here PQRS, closed loop is there. Okay. Now what I will do here, I will divide into parts. So see here please. First I will write here P2Q and it is B dot dl. Is it? P2Q B dot dl. Next one P2Q. Then where to where? Q2R. Q2R B dot dl. Okay, Q2R B dot dl plus after that Q2R, then R2S. R2S B dot dl. Is it? And after that what will happen that here? H2P. Here H2P. And what will come here? B dot dl. Is it? And equal to mu naught into I enclosed here. Now this thing we have got it. Now after that, just let me write here. See, like this. Now what will happen that here? See here. Now we have to see P2Q. So P2Q magnetic field in which direction? Right side. And this Amperian loop direction is which side? This side. So vector B also right side. Even vector DL also right side in the same direction. That's why I have taken same direction. Okay. So what will happen that here? See, this P2Q, it will become here B dl cos 0. B dl cos 0 because both in which direction? Same direction. After that, see here Q2R. Q2R, you think what will happen that here? If you will see Q2R when we'll go here, you can see very well. This is the direction of the magnetic field. Is it? But you can see length in which direction? Length in this direction. See arrow. Arrow. See the arrow. Is it? So see the arrow here. So here it will make how much angle, students? Here you can see how much angle it is making. It is making here the 90 degree. See, I have just represented here this one here. Is it? So B is this side and the DL is upward. So how much angle is there? 90 degrees there. So I can write here, see, B DL cos 90. Is it? After that, see here, if I talk about R2s, outside the solenoid, magnetic field negligible, or we can tell ideally 0. So if I write here the R2s, I will write here the magnetic field is 0. Okay, 0 dot dl. Plus after that, if I talk about here where to where, H2P. H2P, what is happening that here again you see, if you will go H2P here, see I will represent here magnetic field in this direction, is it? But the dl in which direction? See, this downward direction here, is it? This is the dl. This is B, and this dl downward here also B, this dl upward. Okay, so here also how much angle is there? Here also angle is 90 degree here. Okay, and see I will just write here in see this one here, see. Don't get confused. Here also see I am writing. Okay, so here what we can write here, again we can write here, see, B dot dl cos 90 is equal to mu naught into I enclosed. Is it? Very easy, very easy, very easy. After that, now what will happen that here, we'll go ahead further. So see, if I write, so see, B dl cos 0, so we can write here P to Q, it will become here B into dl, okay, plus cos 90, 0. This is also 0 dot dl, 0. Here also cos 90, 0 is equal to mu naught into I enclosed. Very, very important. See, mu naught into I enclosed. Is it? Now, see, kindly. Very well. So, this thing we are going to take it on a next page. No? This thing we are going to take it on a next page. So, what we can write here? See, here we can write, this is the integral P to Q B dl is equal to mu naught into I enclosed. Okay. After that, next one, you know, magnetic field is constant, uniform. So B will come outside and integral PQ dl. Is it? And after that, what is this? Mu naught into what is I enclosed? Here you can see, during the calculation of the magnetic field, if only one turn is there, we will use just I. If in case two turns are there, 2I, 3 turns, 3I, is it? So like that, here also if you will see that, inside the rectangular Amperian loop, can you see only one turn is there? Just for the representation purpose here, 3 turns are there, is it? So it does not mean that we will write here I enclosed 3I, no, we will just calculate by the unity rule, is it? How we will calculate by the unity rule? Remember that here, what is the length of the solenoid? Length of the solenoid is a L, okay? So kindly see here, L length of the solenoid is carrying how many ampere turns? Ni. Total number of turns is N, current is I, so we can write here Ni, is it? And small, is it? After that, if I write here the unit length will carry how much here? See, N by L into small I, is it? After that, if I write here the, what is the length of the Amperian loop? Small L. So that one will carry how much here? See, N by L into small I into L, is it? So this thing you have to remember that here, okay? And what is this? This is the I enclosed. What is this? This is the I enclosed. Now remember that here. And what is N by L? N by L. Okay, let me write here. Now I enclosed, I can write here. See, N by L into I into small L. Okay. So now we can write here C, and integral P to Q. What is the length? See here. P to Q, what is the length? Length of the Amperian loop is L, is it? So I can write here, see, B, and L is equal to mu naught N by L, is it? And after that here, I into L. So both the sides, what will cancel out here, students? This L and this L cancel out here. That means this magnetic field, whenever we are calculating, this magnetic field calculation is independent of shape and size of the Amperian loop, that we have learned under the important point, because both the sides L cancelled out, is it? That means the magnetic field inside the solenoid is given here mu naught N by L into I. What is N by L? Number of turns per unit length. So mu naught Ni here, is it? So this is the magnetic field. Okay, kindly see here, I am writing in a bracket. Very, very important, is it? So see, mu naught Ni, uniform magnetic field. And as I have did not tell you, but basic you know very well. What is the basic? Inside the solenoid, what is the medium? Here, what is the medium? Nothing is present. So what is the medium? Air is there. What is there inside the medium? Air. Further we can put other materials also like dia, para, ferro, but as of now air is there. And what is this mu naught? Mu naught is called the permeability of free space, and this mu naught value is used to be how much here? 4 pi into 10 to the power minus 7 Tesla meter per ampere. Okay, remember that here. So we have covered the application 4. Now we'll see here application number 5, very similar to the solenoid. Let's see here. So see, magnetic field of a toroid. So see, what is the toroid here? See, a toroid can be considered as a ring-shaped solenoid. What is the toroid? Can be considered as a ring-shaped closed solenoid. Magnetic field inside the toroid can be written as. Okay. So here what will happen that here, you know, in case of solenoid, two ends are there. So this end and this end, if you connect them together, then what it will happen that here, it will become the toroid here. Okay. Or even we can tell endless solenoid also. Okay. Or we can tell ring shaped closed solenoid here. So here you can see very well, here I have taken here the toroid, is it? So inside the toroid, what is happening? See. So inside the toroid, what is the shape of the magnetic field? You can see very well. The circular magnetic field will be there, concentric circles, is it? Let's take inner radius. No, this is the toroid, ring shaped, inner radius R1 and outer radius is R2, is it? And here what will happen that here the current will flow. Let's take from here the current entered I current entered. So it will flow, no? It will flow like this and then it will go like this, is it? See this current is flowing like this, no? Like this current is flowing here at all the turns. So because of this current, what will happen that here? Because of this current, what magnetic field will exist? And remember that here concentric magnetic field is there and this magnetic field is non-uniform. Why non-uniform magnetic field is there? Non-uniform magnetic field. Why? Because uniform magnetic field means it should be straight line and equidistant. Maybe here the magnetic field is equidistant, but this is not a straight line. That's why the non-uniform magnetic field is there because of the direction consideration. Okay. And in the same way, if we write here the magnetic field, so magnetic field it is given here B equal to same story mu naught Ni. What is this will become here? Here also it will come same B equal to mu naught Ni, because as I have told you, magnitude wise it is same. Only the direction is getting changed. And what is N? N is the number of turns per unit length. But here length is not there. So here instead of length, what is there? The circumference is there. Okay. And the length of that circumference is given here 2 pi r. What is this? 2 pi r. And here what I have written here? Here I have written here Rm. Why I have written Rm? Because Rm will be the mean radius. What is the Rm? Rm will be the mean radius. And this mean radius is given by R1 plus R2 by 2. Is it? What is the Rm? R1 plus R2 by 2. Remember that. Okay. And on the other note, you can see very well magnetic field at the center. Magnetic, sometimes they will ask at the center, and outside the toroid is 0. Okay. So I hope so you understood very well. This solenoid you have understood very well, and this toroid also you have understood very well. Okay. And remember that here for infinite solenoid, this formula we have got for the infinite solenoid is there. That is independent of a radius. What is this? This is independent of a radius. Okay, small r here. Okay. This also have to remember that. For infinite only I am telling. Okay, great. Now students, after that we'll go to the next one, and here you can see the NEET 2020 and even in JEE 2023 also same kind of questions they have asked. What is the question? See, a long solenoid, that means by default infinite, of 50 centimeter length having 100 turns carries a current of 2.5 ampere. The magnetic field at the center of the solenoid is how much here? Okay. So we'll note down the data. The data is what? The number of turns, how much is given here? 100. Okay. After that, what is the length of the solenoid? Capital L. It is given here 50 centimeter. Is it 50 centimeter? So we can write even 50 into 10 to the power minus 2 meter. Okay. Then after that here they are carrying how much current? The current is given here 2.5 ampere. Okay. And they are asking magnetic field inside the solenoid. Okay. And whenever air medium is there, na, instead of B, even you can write B naught also. Okay. So I will write here this B naught. Is it? Even in previous cases also, wherever this B is there, na, this B you can consider B naught, because which medium is there? Air medium is there. Okay. So this B naught is we have to calculate here. Okay. So first let me just calculate for you. Very easy. Let's take here small n. What is small n? Number of turns per unit length. So Number of turns, how much is given here? 100, is it? And you can see very well. Length, how much is given here? 50 into 10 to the power minus 2, or I can write here 5 into 10 to the power minus 1. Okay, so it will become here 1000 by 5, or we can tell here 200. How many turns are there? 200 turns per meter. 200 turns per meter, is it? In the solenoid is there. Okay, again if I talk about here the magnetic field, nothing is given, air medium, so B naught is given by mu naught n into I. What is mu naught? Mu naught is given here 4 pi into 10 to the power minus 7. What is small n? It is coming 200, that means 2 into 10 to the power 2. And current, how much is given here? 2.5. Okay, so current is 2.5. Okay, so now after that here, just let me see here, see, this is 4 into 10 power minus 7, this data and this data is there, is it? So now we'll simplify this here. Let's collect first this numbers. So 2.5 into 2, 5. 5 into 4, 20. So 20 pi, correct? 2.5 into 2, 5. 5 into 4 pi, 20 pi. Powers if you collect it, 10 power minus 7 and 10 power 2, it will become here 10 to the power minus 5, is it? Or we can write here, see, 2 pi into 10 to the power minus 4, or 2 pi means 2 into 3.14. So 2 into 3.14 means 6.28 into 10 to the power minus 4. Unit of the magnetic field is Tesla, is it? So which option is matching here? You can see very well. The correct option is here. Option D is the answer. Is it? Make sure that sometimes they are giving, as it is given in this question, length of the solenoid in a centimeter. Okay, so only we have done that. Okay. And radius is not given, so anyhow infinite length solenoid is there, as I have told you, independent of the radius. But here what is this? This formula is valid when this L is greater than R. Okay, maybe 40 times, 50 times, like that is there. At least it should be more than 10 times, then only we can tell. Next one, let's see. This question is there. What is the question? See, came in a NEET 2023 and important for JEE also. See, a long solenoid carrying a current produces a magnetic field B, that is given here, is it, along its axis. If the current is doubled and the number of turns per centimeter is halved, the new value of the magnetic field is how much is there. Okay, so initially what is given here? Initial magnetic field, it is given B, and after that what they are telling, the current, let's take the initial current is I, so see I1 is I, okay, and the number of turns per centimeter, what is given here, let's take here N. This is the scenario. After that, in next scenario, what is happening, let's take here new magnetic field B2, we have to calculate, and the current, what is happening that here, current, what they are doing here, if the current is doubled, so instead of I, it will become here 2I, is it? And the number of turns per centimeter, what is happening that here, it is halved. Halved means what is happening that here, N by 2, is it? So after that, if I write here, see, after that, if I write here, see, as B equal to mu naught Ni, this is the formula. Hence, if I write here, see, this B2 by B1, how to get it here? We have to get the proportional formula. So this B is directly proportional to mu naught is constant, medium is same, so I can write here N into I here. What is this? N into I, is it? So we can write here B2 by B1 means we can write here, see, N2 by N1 into I2 by I1, is it? After that, what will happen that here, see, what is N2? N2 is what here? See, this is N2. This is N2. N2 is what here? N by 2, is it? By N into. What is I2? I2 is 2I and this is I. So anyhow, what will happen that here? You can see very well here. This I cancel, this and this N cancel. What is left here? 1 by 2 into 2. And even what will happen that here? This 2 and this 2 also cancel, is it? So we can tell here very easily, this B2 is equal to B1, or hence we can tell here this new B2 is how much here? B. Okay. So which option is correct here? The correct option is here, option B. See, here I have solved, because we have to solve in an exam, in a CBSE based exam. In a NEET and JEE exam, by the common sense also you can do very well. Like this N is becoming what? N is becoming directly you can do here. This N is becoming what? N by 2 new. and the current is becoming 2I, and what will happen that here, common sense, this 2 and 2 will cancel, so magnetic field will be unchanged. No? But this thing we can do in a NEET and JEE exam, but in board exam we have to write like this, is it? Next one here, students, this one. So here the question is what, see, two toroids 1 and 2 have total number of turns 200 and 100 respectively, with average radii 40 centimeter and 20 centimeter respectively, is it? If they carry same current I, okay, they have given capital I, but I have taken small I, ratio of magnetic fields along the two loops is how much here? Okay, so first note down the data. So they have given here number of turns, N1 what is given here, 200, okay, and this side I will write here the data. Second one, N2 how much is given here, 100. Now next one, what they are telling that here, average radii for 200 radii they have given here 40 centimeter average, okay, so I can write here mean radius, RM1 mean radius, how much is given here, 40 centimeter, okay, and here what is given here, RM2, it is given here 20 centimeter, is it, 20 centimeter. After that they carry the same current, that means we can tell here, okay, I1 is I, or here also, okay, they are given capital na, so I2 is I. So what we can tell here, from here we can tell I is constant. What is I? I is a constant. I is a constant. So what they are asking the ratio of the magnetic field. So anyhow they want to know that what is the B1 by B2, is it? This is the scenario, this they want to know, okay. So what is the formula? Formula we should know very well, no? The formula is very easy, see, as B equal to mu naught small n, that means capital N by 2 pi Rm into I, okay. They have given capital I, so I will write here the capital I, okay. But make sure that always you try to write small I, that is better, okay. So that later you will not confuse with the intensity of magnetization that we will learn in a next chapter, okay. So here what will happen that here, if you will make here the proportional formula, so what is the proportional formula will form here, the proportional formula will form here, if I write here, this proportional formula will be B directly proportional to N by Rm. What will happen that here, this will be B directly proportional to N by Rm, is it? So now after that here, see, hence what we can write, hence this B2 by B1 is equal to, we can write here, see, N2 by N1 into, it will become here inversely proportional now. So B2 by B1 means Rm1 by Rm2 here, is it? And after that just put the values here. So see, N2 by N1 what will come here, see, N2 is 100, N1 is 200, so we can write here, see, 100 by 200 into, what is Rm1? Rm1 is 40 centimeter, anyhow the centimeter will cancel out, no? Because all the time no need to convert into SI, is it? You have to think, if it is going to be cancelled out, no need to convert. Even if you write also 10 to the minus 2, that will also cancel out. Why to make the calculation complex? And what is Rm2? That is the 20, is it? So when you will simplify this, 100 by 200, it will come here 1 by 2, 40 by 20, again it will come here 2, and what will happen that here, this 2 and 2 will also cancel out, is it? So we can tell here, this B2 will come here B1, B2 will come here B1, and what is the B2 by B1, B2 by B1, B2 equal to B1. So ratio B2 by B1 will come how much here? Or they are telling now first to second solenoid, na? So B2 equal to B1, so we can write here hence B1 by B2, na? Because they are mentioning first solenoid then second solenoid, nothing is mentioned, so B1 by B2. Anyhow, B1 by B2 also how much will come here? Again it will come here same only, whether you tell B1 by B2, B2 by B1, 1 by 1 only. But according to the question, first they mentioned toroid 1, toroid 2, so B1 by B2, okay. First B1, second B2 according to the question. Which option is correct here? The correct option is here, option A is the answer. Is it? Great. Now students, after learning all these things in finite solenoid, toroid and problems and all, now we'll see here the magnetic field inside the finite length solenoid is there. Okay, so here again in the same fashion I have taken here one solenoid, okay, and this is one end of the solenoid and the end of the solenoid, okay, and anyhow the length of the solenoid, how much here? The length of the solenoid is L. Length how much here? Length is L, and it's a radius. It's a radius here, right here. This is a radius. Radius what we write here? Small r. Okay. Now after that here, when the solenoid is which length? Solenoid is the finite length. Okay. So let's take here from this end of the solenoid we will connect to the point P, okay, and here also the point P is inside. From here also we will connect to another end is there, okay. After that what will happen that here we will draw here one vertical line now passing through this like this as much as good possible, okay. And let's take here, students, if I write here the angle, okay. So let's take this angle is alpha and let's take this angle is beta. Now angle we are seeing from here, this is the reference, okay. So in this situation, remember that here, if the number of turns of the solenoid is the n, total number of turns n, length is L, and number of turns per unit length is small n. That we know very well, okay. So in this situation, the magnetic field inside the finite solenoid is given by, remember that here air medium, you can write B naught also, but I will write B, okay. So B equal to mu naught Ni by 2, and it will become here sine alpha plus sine beta. What will be there, students? Sine alpha plus sine beta, is it? And you can put into the box also even here like this here, is it? So this is the formula, mu naught Ni by 2 sine alpha plus sine beta, okay. Sometimes if angle and all is not given, they have just given length and radius, is it? So in that situation what will happen that here we will just make sure that we will just consider that by default alpha is equal to beta if angles and all is not mentioned, okay. So in this situation what will happen that here, if alpha equal to beta, we can write here mu naught Ni by 2, and beta will also become alpha, so sine alpha plus sine alpha, it will become here 2 sine alpha, okay. And hence what we can write here, this B will become here mu naught Ni, anyhow 2 cancel, what we can do here, this 2 and 2 is a cancel, is it? So we can write here mu naught Ni into sine alpha, okay. So this thing also kindly remember that here, okay, and this is the one formula, this is the formula, okay. But now what is the value of the sine alpha? Sine alpha value, no, that also we should know, no. So sine alpha value how much here? If you take the triangle, now if you take the triangle, now let's take, I have taken this triangle is there, now. Sine alpha means what? Opposite by hypotenuse. So in this triangle, this is the opposite, this is the adjacent, this is the hypotenuse, is it? So what will happen that here, sine alpha will write here, see, if the total length is L, this length how much here? L by 2, is it? And after that here, what is the hypotenuse? You know very well here, from here to here, length how much here? L by 2, and this length, now see the radius is R, so this length is also how much here? R. So what we can write here, if we calculate the hypotenuse, it will come here, see, L by 2 square plus R square, is it? So when you will simplify this, see I will write here, this side here, so when you will simplify this sine alpha will come here L by square root of L square plus 4R square, okay. Have to just simplify this, you will get this, okay, you will get this very easily, remember that here, this sine alpha here, okay. If sometimes angle and all not given, they are just writing the length and the radius, sine alpha you can use this also, okay, great. Now students, after that here, if we talk about here the some cases of the magnetic field of the solenoid, okay. So see here the first case, what, see, if the solenoid is of infinite length and the point is well inside, then what is the alpha and beta value? So you think when the solenoid length is keep on increasing, say here from this reference line, when the solenoid is the keep on increasing, see the alpha value will keep on increase, and for infinite length alpha will become how much here? 90 degree. What is the alpha? It will become here 90 degree. Similarly this side also, when the length will increase, this angle will also keep on increase, okay. And for infinite solenoid means here beta also 90 degree. Infinite means left side also infinite, right side also infinite. That is called the infinite. Semi-infinite means one side infinite, but another side is finite, okay. So alpha is 90, beta is 90, then magnetic field will come how much here? See, this B, and here we can write here the B infinite solenoid, is B I means infinite, or we can write here IN, B infinite, INF, B infinite. So alpha is 90, beta is 90, sine 90 plus sine 90, 1. See here, I write mu naught Ni by 2, sine 90, 1. One more sine 90, 1. So 2 by 2, it will cancel out. So B infinite, it will come here mu naught Ni. Is it? And even that I have told you. Is it? Remember that here. See here. Okay. Great. Now students, after that what we'll see here? See this one, the second case. What is the second case? See, second case. if the solenoid is of infinite length and the point is near one end, then alpha and beta value how much here? Now you think here, if this point P is there, na, this point P is there, na, this point P is at one end, okay? So what will happen that here, point P is at one end. So what you can do, maybe this point P you can take from here to here, or what we can tell, this solenoid I will just take this side so that the point P should come at one end. So you think here, if solenoid I am just making it point P is at one end, na? So this side solenoid is there, beta is 90 degree, no problem, but see this end I am taking here. So see, this alpha value is keep on decreasing, and when it will reach here, is it? So that time alpha value will be how much here? Alpha value will be 0 degree. Alpha value 0 degree, beta how much here? 90 degree. Again I am telling you here, see, this is there, na? See, this is there, na? See, I am writing here. Is it? And what will happen that here? See, anyhow here, just for your understanding purpose only I am telling. Is it? See, like this. Now point P will be where? The point P will be at one of the end. Is it? So see, here is the point P at one end of the solenoid. This side also solenoid is there, no problem. This side also solenoid is there, but here point P is here. So you can see very well here all the angles we are seeing from here. Is it? Like this here. And when we will take here the angle, na, angle in this will be there, na, see, like this. So in this what will happen that here, this alpha will become here 0 degree. Getting? I hope so this is very clear. Okay, alpha will become how much here? The alpha will become here the 0 degree, na? Like this it will keep on decrease, and then it will become here 0. And this side anyhow, beta how much here? Infinite. Is it? So in this situation what will happen that here, students, this magnetic field B is given here, see, mu naught Ni by 2, and here we can write here, see, sine 0 plus sine 90. Okay, so hence this B we can tell here at the end of the solenoid, B end. Okay, so this B end will become what here? Mu naught Ni by 2. Is it? B end will become what here? Mu naught Ni by 2. Even we can tell here this is the semi-infinite also. Which solenoid is there? Even we can tell here semi-infinite. Why semi-infinite, students? Because one side, right side, it is infinite, but this side no solenoid is there, so that is called the semi-infinite. And here alpha how much here? 0. And beta how much here? Beta is 90 degree is there. Is it? So this is the thing. After that, if we draw here the B versus L graph for the solenoid, you know very well, inside the solenoid the magnetic field was B naught Ni, but when we came to the end, what is there? Mu naught Ni by 2. Okay, so length of the solenoid is the L. This side I have taken plus L by 2. This side also I have taken minus L by 2, na? Plus L by 2, minus L by 2. From the mathematical graph, na? Mathematical what we call coordinate axis. So total length how much here? L. So you know how the graph looks like here? The graph looks like something like this. Here means we'll write here this B, that means mu naught Ni. Is it? So graphs here. And here what is this? At this point, if I write here, see, like this. Like this. And this side what used to be there? It used to be mu naught Ni by 2. Okay. What used to be there? Here mu naught Ni by 2 at this point. Here mu naught Ni. This side mu naught Ni by 2. Okay. So if I draw here the graph how it will look like here? See, like this. From here it will start. Some constant, then you can write here like this, it will go. Here also you can see somewhat uniform magnetic field like this. Like this. Is it? So like this the graph used to be. Is it? Okay, so kindly see very well. Is it, students? So I hope so. This video based upon the solenoid, toroid and the question is very clear to you. Keep studying, keep growing.